Suppose you have some shape, like this snake, described underneath by a triangular mesh, and you'd like to animate it. One very simple way of doing this is to pre-specify a few control points on the snake, and then let the user drag these around. Technically this works, but as you can see, the results aren't necessarily very compelling. Example-based mesh deformation aims to address this by instead taking multiple different shapes as input, which I'll color code here to better show what's going on, and then using the range of features observed with these different inputs to inform the deformation. So here in this animation, the color shows which of those different input shapes are most influencing the result, and this can make a big difference in terms of quality. Now this in itself is not a new idea, so if you're familiar with the research area, you might be wondering why we need another paper like this. In short, the goal of this work is to describe a technique which just works, across a wide range of examples without any need for parameter tuning. And in particular, we're also going to want it to work even for highly stylized and cartoony inputs, such as some of those you see here. To do this, we'll need to achieve three things. Firstly, we'll want the method to be reliable, and that it always uses the artist-provided inputs in an intuitive way. We'll also want it to be expressive, in that a wide range of different deformations can be generated from just a few inputs. And we'll also want it to be fast enough to run in real time. And I'll spend most of this talk just talking about the first point up here, because I think it's maybe the most likely to be useful in other contexts, and because I can provide the additional benefit of giving some background intuitions which didn't make it into the paper. Existing approaches for solving this sort of problem roughly fall into one of two categories, the first of which I'll refer to as energy interpolation, and the second of which I'll call Shapespace approaches. But before I describe these, I think it's useful to talk about the lens through which we view this problem, so that I can properly frame these approaches in that context. After this, hopefully our approach will actually seem relatively obvious. In short, our method is based on looking at this problem as a combination of two things: mesh deformation and scattered data interpolation. But let me begin with some notation. A standard non-example-based mesh deformation takes as input some shape, I'll denote that with P, and after the user has moved some control points around, you also have a deformed shape, which I'll denote with Q. The deformation is driven by an elastic energy, which describes the amount of bending, twisting, and stretching you need to transform P into Q. In our case, the deformed shape is generated by minimizing this elastic energy subject to a set of constraints derived from the user-specified control point positions. So let's think about how this should ideally behave for this input shape up there as the user drags this rightmost control point around to different positions. This is a standard mesh deformation problem, so you'd expect results something like you see up here. Of course, if you'd picked a different input shape, you'd expect correspondingly different results. But what if you have multiple different input shapes at once? Now you need an example-based elastic energy. And for notational convenience, I'll take the set of all the input shapes and just denote this with a capital P. As before, you also have your deformed shape. An example-based elastic energy is then a function which takes as input the set of all these input shapes, the deformed shape, and also this additional vector of what I'll call blend weights. These denote how strongly each of the different inputs should influence the result. And throughout this talk, I'll implicitly assume that these blend weights are constrained to be non-negative and to sum to 1. So let's think about how this should ideally behave for these inputs that you see, which are kind of going to be a running example of this talk. Well, from these, I think it's obvious what the artist would want to happen, which is, as the user drags this rightmost control point out, the box first puffs outward and then thins inward. So this actually looks a little bit like scattered data interpolation, where you want to use the red input around here, the green input around here, and the blue input around here, and the rest of the space should somehow smoothly interpolate between these values, which is what our method does. So you can kind of see, summarized this image up here, that the behavior you ideally want out of this simultaneously combines aspects of both mesh deformation and scattered data interpolation. Now, we're going to need to keep this mesh deformation problem in the back of our minds, but I think it's actually simplest to proceed by temporarily putting it aside and thinking of this just as a pure scattered data interpolation problem. Accordingly, I'm going to represent each of those input shapes with just a single dot in the 2D plane. Given another point, abstractly representing the deformed shape, a standard non-example-based elastic energy is then roughly analogous to, say, measuring distances in this 2D space, or maybe square distances or something. I think it's informative to look at how the analogs of existing approaches for example-based mesh deformation perform in this simplified context. So let's start with what I'm going to call energy interpolation approaches. Ignoring all manner of details, these take a common form, where given your input shapes and your deformed shape, you first measure the elastic energy between the deformed shape and each of your inputs. The final example-based elastic energy is then just a weighted sum of these individual energies, which of course is minimized by putting all the weight on the smallest distance and 0 on the rest. For this reason, this kind of formulation is normally used for the problem of shape interpolation, where these blend weights are fixed in advance and are not solved for by the optimization. But let's look at this as a scattered data interpolate first. And to really make this a scattered data interpolation problem, I'm going to associate a data value with each of these points so that I can visualize how this value is interpolated across the rest of the space. And I'll animate this as that center point's vertical position is changed. So based on my description, you get about what you'd expect. This just corresponds to interpolation by projection into the nearest Voronoi cell. And this obviously has the artifact of these hard, discontinuous transitions in the interpolated function, and this carries across to mesh deformation too. To illustrate this, I'll draw a little visualization, where on the top, I'll show an animation of this running example as the user drags this rightmost control point out and then back again. And on the bottom, I'll visualize the blend weights, each color-coded by the input shape that it's associated with. And the x-axis here is time, which again is drawn as that rightmost control point is dragged out and then dragged back again. So here you can clearly see the artifacts resulting from this discontinuous way in which the different inputs are treated. And not surprisingly, this causes artifacts for slightly less canned examples such as this cartoon caterpillar here, where you can clearly see the discontinuous transitions. And this is an example which our method handles a lot better, as you can see up here. But of course, there's a second class of existing approaches which you probably would be much more likely to use for solving this sort of problem, called Shapespace approaches. And I'm borrowing the term Shapespace from Sumner et al. Other authors refer to an analogous concept as an example manifold. And these take a different form, where given my input shapes, I first form the space of all convex interpolations of these shapes. Now often this interpolation is done in some higher dimensional nonlinear feature space, so I'll just use the blend function there on the bottom to abstractly represent some way of interpolating between my input shapes based on the blend weights in this vector B. The final example-based elastic energy is then defined such that minimizing it roughly corresponds to finding the minimal distance between my deformed shape and some point in this shape space. So with the case of example-based mesh deformation, the properties of the deformed shape are largely governed by the properties of the nearest point in the shape space. So let's look at how this behaves as a scattered data interpolant. At first, it seems to be a lot better, but you'll notice some problems. In particular, very small changes in my inputs can lead to very large changes in the interpolated function. And there's also situations where this interpolation is ambiguous, in this case where those 3 points are collinear. And of course, in a simplified 2D example with more than 3 points, this ambiguity would be a much more severe problem. These artifacts also carry across to mesh deformation, although things get a little more complicated because how it behaves depends on if the shape space is a linear or a nonlinear function of the input shapes. So let's start with the case where the shape space is linear. Here, that ambiguity problem I mentioned is out in full force, and in this example, the green input is basically completely ignored. And that also causes problems for slightly more realistic examples, such as this chameleon. With this linear shape space approach, this chameleon doesn't open its mouth like the artist intended. And again, this is an example which our method gets right. But in practice, it's slightly more common to have the shape space be nonlinear. So let's take a look at that. Well, there's little here in the way of hard guarantees, but it turns out this ambiguity is a bit less of a problem in practice. However, the nonlinearity introduces problems of its own. For example, you can get discontinuous transitions as the optimization switches from one local minimum to another, or you can get stuck in a bad local minimum. And this causes problems. Also, I'll illustrate this on a piranha plant example. You can see that the artist was going for this nice chomping motion. But with this nonlinear shape space approach, you don't get it. Basically, the optimization just stays stuck in a bad local minimum. It turns out this also happens with that chameleon example I showed earlier. And again, our method gets this example much better. So what is our method? Well, if you look at these two pre-existing methods of shape spaces and energy interpolation, you'll see that their strengths and weaknesses are actually sort of complementary. So our approach is basically just to sum them together. Said it would look kind of obvious. Actually, this is ignoring a technicality which I'll get to in a bit, but let's go with it a bit and look at this as a scattered data interpolant. And the easiest way to do this is to base this on a squared elastic energy, or in our simplified example on squared distances in the 2D plane. And that gives you this. You'll see there's no more issues with ambiguity, and there are no discontinuous transitions. But there is one potential issue, and that's these plateaus around each data point. Now, depending on your application, this may or may not actually be an issue, but we choose to mitigate it anyway. We do this by switching to a non-squared elastic energy, which brings you from this to this, where those plateaus are gone. And here's that animation I've been showing one more time for this case of a non-squared underlying energy. So that basically works like you'd want, except you notice this discontinuity here. This turns out to be an artifact of the fact that using non-squared distances here gives an objective function which, although it is convex, is not strictly convex. So it actually is possible to fix this. Both mesh deformation, we actually haven't observed any serious artifacts resulting from this, so we actually leave it as is to get a slightly simpler algorithm. Now you may recall earlier I mentioned that there was a technicality that I was temporarily ignoring, so it's time to take a look at that. And this comes from the fact that scattered data interpolation assumes you have the separation of your data into a domain and a range. With mesh deformation, you don't have that. You just have meshes. So this idea of interpolating the value at each data point based on the position of that data point isn't actually quite so simple. But it's possible to tweak this example to account for this, and to do that, we'll remove the distinction between the position of a data point and the value associated with it. That brings you into a three-dimensional space like this, where the z-coordinate of each point is just equal to the data value associated with that point. So you can see here that distances in the three-dimensional space do not correspond to the distances in the 2D plane that we wanted for scattered data interpolation. But you can fix this, and to do that, in this case, we'd solve for the z-coordinate of Q such that it minimizes the distance from the data point we're interested in. After this, that three-dimensional distance exactly matches the distance that we wanted for scattered data interpolation purposes. Now, of course, with mesh deformation, everything here is a much higher dimensional manifold. These distances aren't Euclidean. Actually, they're not even guaranteed to be a proper distance metric. But because we didn't stray too far from traditional mesh deformation approaches, and we didn't take this scattered data interpolation metaphor too seriously, it turns out that everything basically works without further modification. So that brings you from this to this, which is our actual non-simplified formulation. And it might look like this nested minimization here would be cause for concern, but you can rewrite this to pre-compute these values, after which it simply amounts to adding a carefully crafted linear term to the objective function. So it doesn't actually cause any problems for optimization. The application of this to mesh deformation is actually very straightforward. Given your input shapes and the user-specified control point positions, you first independently deform each of these input shapes to match those control points. The amount of deformation required of each shape in this process is then used to penalize any usage of that shape in the final blend. So this removes the issues of ambiguity that we saw earlier when the shape space was linear, giving what I think are more or less the transitions that an artist would intuitively expect from those inputs. And it also works much better when the shape space is nonlinear, although I should admit this is partially due to the fact that you have more algorithmic freedom since you no longer have to depend on this nonlinearity to resolve the issues of ambiguity. Now, our full algorithm is based on taking these ideas and applying them to an as rigid as possible elastic energy. And there's much more to it than I just described, but I don't have time to get into it in detail. Suffice to say that we form a linear blend subspace consisting of changes in geometry and shape, operate on large clusters of triangles at once for efficiency, and do a whole bunch of work to spatially localize the way that the different inputs are used in the deformed mesh. But I'll just go on to results. Here's 3 simple inputs describing a starfish. Put those into the system and you get a nice little model you can play around with in real time. And it might not be immediately obvious, but this model actually gets quite a bit of benefit from these spatially localized blend weights that I mentioned. So although I didn't get into the mathematics of this, you can see the effect that it has and the extra expressiveness that's added to our model by being able to use different parts of different inputs in different parts of the deformed mesh. This is particularly helpful when dealing with articulated characters like this horse, because it lets you independently manipulate the different limbs of the creature without worrying about adding the sorts of artifacts that you can expect from globally constant blend weights. So here, the front legs and the back legs of this horse are using different input shapes, which you need to, if you don't do this, you get some very unnatural bending artifacts in the legs of this horse. You can also see this at work in this face deformation example. In this case, also benefits a lot from these this linear blend subspace and operate on large clusters of triangles, such it actually lets our method run at a speed which is independent of the resolution of the input meshes, which is good because otherwise this wouldn't run anywhere near real time. And here's a final example of a lion, which I like because it nicely illustrates how our method reliably and intuitively uses the different artist-provided input shapes, only here with a 3D example instead of the 2D ones I've been showing previously. So in conclusion, we've described a method for example-based inverse kinematic manipulation of meshes, which reliably and intuitively uses the input shapes by using elastic energy combining ideas from both mesh deformation and scattered data interpolation. We increase the expressiveness of our method by allowing the way in which the different inputs are used to spatially vary across the deformed mesh, and we made our method run in real time by using a formulation which runs in a complexity independent of the resolution of the input meshes. Thank you.